We all depend on reliable power.
Right.
It's fundamental.
Absolutely critical.
And while we often focus on the big national grid, there's this quiet revolution happening.
Right, with these localized power hubs, microgrids.
Exactly. Microgrids. They promise so much, but they also bring some surprisingly tricky challenges for keeping the lights on.
They really do.
Today, we're definitely diving deep into those complexities. Okay, let's unpack this.
Yeah, so a microgrid, essentially, it's a sophisticated, self-contained energy system.
Like a mini grid for a neighborhood or a campus.
Precisely. Think local generation, maybe solar panels, small turbines loads, and crucially, energy storage.
Okay.
And what makes them so revolutionary is this dual capability. They can be connected to the main grid, sure. But the critical part, they can also switch into islanded mode if there's a big outage.
So they keep power flowing locally even if the main grid is down.
Exactly. And that means huge advantages. Consistent power access, better power quality.
Less flickering and surges, maybe.
Yep. And reduced emissions because you integrate more renewables locally. Often lower costs, too. Less need for those long, inefficient transmission lines.
That sounds like an absolute game changer for energy resilience, honestly.
It really is.
But knowing how complex power systems are, I'm guessing it's not all, smooth sailing. What's the big hurdle?
You've nailed it. The benefits are massive, but microgrids introduce some serious protection issues.
Protection issues,
Yeah.
like safety systems.
Exactly. Traditional grid designs, they just weren't built for this. Think of the old grid like a one-way street.
Yeah.
Power flows from big plants outwards. Simple enough.
Right, predictable.
Microgrids, though, they're more like complex city intersections. Power can flow in multiple directions.
Depending on where solar is generating or who's using power.
Precisely. Plus, their internal layout, the topology, it can actually change. It's not always that fixed tree structure. Sometimes it loops back on itself.
Okay, that sounds complicated.
It is. This constant change in flow and layout means fault currents. The surge when something goes wrong, they vary wildly.
Making it tough to even detect there is a fault, let alone figure out what it is.
Incredibly difficult, yeah.
So our old safety rule book, basically, it's out the window.
What's fascinating here is how badly the conventional tools struggle. Your standard overcurrent relays.
The traditional circuit breakers.
Kind of. They assume that one-way power flow, those preset conditions, they're just not adequate for the dynamic two-way nature of microgrids.
So they might trip unnecessarily. Or miss a real fault.
Both. They might see normal operations as a fault, or worse, switch off perfectly healthy sections, causing needless blackouts. It shows we need a smarter, more adaptive approach.
A fundamental mismatch, it seems. Okay, this is where our deep dive gets really interesting, then.
Right.
We're exploring a really cutting-edge strategy, an intelligent data mining-based approach designed specifically for these microgrid protection problems.
But moving beyond the old limitations.
So how does this intelligent data mining approach actually work? How does it tackle these complex challenges?
Well, it starts with some clever signal processing. It uses something called the Hilbert transform.
Hilbert transform. Sounds advanced, like giving the grid superhearing.
That's a great analogy, actually. It lets the system detect these tiny, almost hidden variations in the voltage and current signals.
The very first whispers of a problem developing.
Exactly. The earliest warning signs.
Okay, so you extract that subtle information. Then what?
Then that data gets fed into two powerful AI tools. First up is logistic regression.
Machine learning?
Yeah. Think of it as the rapid first responder. It's trained to quickly and accurately decide, is there a fault here? Yes or no.
And how accurate is it?
Get this. 99.29% accuracy in just detecting a fault exists.
Wow. 99.29. That's incredibly precise. Moving from just reacting to outages to actively preventing them.
It really is. Reducing downtime, saving money, all of that.
Okay, so logistic regression flags a fault. What's next? Does it know what kind of fault?
That's where the second tool comes in, Add a Boost.
Data boost.
Yeah, another machine learning technique. It acts like the specialist detective. It takes over and precisely classifies what kind of fault it is.
Like, is it a short circuit or something touching the ground line? That sort of stuff.
Exactly that. And it does this classification with 98.75% accuracy.
Almost 99% accuracy again. Why is knowing the specific type of fault so important?
Because it lets operators take surgical action. Isolate only the problem section, fix it, and get power back on much, much faster.
Targeted response, not just a blunt switch off.
Precisely. And what's really impressive, the whole system is robust.
Meaning?
Meaning, even with significant noise in the measurements, think static on a radio line, what engineers call 40 dB white Gaussian noise, the system still works.
It cuts through the interference and maintains that amazing accuracy.
It does. Extremely reliable, even under imperfect conditions.
Okay, incredible stuff. So what does this all mean for you, our listener? How does this high-tech solution translate?
Well, if we connect this to the bigger picture, this research offers a simpler, more efficient, and crucially, a highly reliable way to protect this vital microgrid infrastructure.
Simpler even with all this AI.
Simpler in outcome and operation compared to kludging old systems. It means better power quality, more consistency for everyone. It makes our increasingly distributed energy future not just greener, but significantly more resilient, more dependable.
So fewer surprise outages, more stable power from local sources.
Basically, yeah. It's about making sure your lights stay on, your devices work, critical services keep running, even if the main grid has issues.
It really makes you think, doesn't it? This powerful combination, this marriage of advanced signal processing and machine learning.
Yeah.
It's proven so effective here for microgrids.
Yeah, the potential is huge.
Where else could we apply it? How could it enhance safety and reliability in other complex dynamic systems we rely on every day? Optimizing traffic in smart cities, ensuring precision in critical industrial processes. The potential seems to go way beyond just electricity.
Absolutely. Anywhere you have complex signals and a need for high reliability.
Definitely something to think about. Until next time on The Deep Dive.